Well, good morning, dear. Welcome back. And you have started watching video on machine learning. Today we are discussing the concluding part of principal component analysis. As you know, it's a very useful tool, very easy to understand when you have large dimensional data and you have no idea about the pattern of the data. Then it turns out that you can run principal component analysis, which is basically does the eigenvalue decomposition of the covariance matrix. PCA only does this. It is not doing any classification, not finding any pattern, just it is telling you that these are the direction where the variance is maximum. Okay. And that eigenvalue decomposition of the covariance matrix gives us the eigenvector together with the corresponding eigenvalue in descending order, so that we can see which one is important, which are the up to what importance level we can go, because we will have to now select. Those are called features. We can call them feature now, that eigenvector together with eigenvalues. So that guides us to select features. Okay, and then for example, if 1000 eigenvalues are there, and I decide that only 100 eigenvalues and eigenvectors I will take, the top 100, and I will neglect others. And by doing so, as you know, we are losing some information, but maybe we can afford, because our requirement is, for example, sending some information through a narrow bandwidth, okay, and or to do some task where all the dimension information about all the dimensions are not needed. So and that's happened actually in data with higher dimensions. So it helps us. Okay. It has advantages. For example, it removes correlated features by doing, and it improves all machine learning algorithms. So whenever you have some data, you can just, and you suspect that there are correlated features, then you can run PCA to remove them. Okay. And also it can, by that process, it can reduce overfitting. However, there is no free lunch, as I say. Disadvantages are, there are some disadvantages. It's difficult to interpret the independent variables, and data standardization is an issue. Means, for example, you have various heterogeneous dimensional data. You are measuring distance in mile. In some data it is measured in kilometer, some data is measured in pound, some data is measured in kilogram, all kind of things. So you will have to standardize the data, otherwise you will get ambiguous result. Okay. And as usual, since we are is a lossy compression, so there will be information loss if selectively we take some eigenvectors and eigenvalues. But even then, it has great applications. For example, facial recognition. Okay, facial recognition in some particular application. Say, for example, you open your a laptop and there is a camera, and you have trained your system that only your face will act as a password. Okay, so you can apply PCA based face recognition system, because it is computationally very friendly. So in such face recognition system, you can actually apply PCA. Image compression, although lossy compression is there, but image compression Because basically what it is trying to do, you have data, it is trying to give you the representation of the data. Okay, and in one sense, by selecting fewer important eigenvectors, you are learning the representation. And for example, you want to send some image, okay, after compressing to your friends. Okay, that is a bandwidth problem. So there is no other alternative. So you just encode the image, okay, and send it because now it is low bandwidth also will be sufficient. Okay, and whoever is receiving, if he is having she or he is having decoder, then that from the encoded information they can reconstruct. Okay, so PCA can help you all this. Okay. In financial data, huge stock market data, for example, bioinformatics data, psychological, social cybernetics data, all data may be huge, and you may not have a good idea that what is important, what is not important. So in first hand, you just run PCA. So that will work. So also finding features from data for classifier design and regression analysis. So you can just select eigenvectors as a feature, and then subsequently you can design your classifier. So isn't it great that it is very computationally efficient, one of the easiest process to understand. However, intuitive idea about what is happening to the data after eigenvalue decomposition, you may not get. That's another issue. That's why I will just going to show you at least because to PCA the data is only in terms of vector, in terms of matrix. Okay, it doesn't understand anything. But if you want to understand that, say for example, I am using the satellite image classification. We have an assignment to do. I have configured it. We have satellite data of, say, river Ganges, okay, where you could see which is river, which is non-river kind of classification. Is a practice problem. So using PCA, you can get ideas about in what band what data is there. Okay, what kind of data is there. So you can just run PCA, and every step, inputting the image, you can visualize it, what is happening. And in the net, you will get many such examples, and with with celebrities' faces, the PCA-based image recognition has been tried, and I am trying to give you one of such idea that how to visualize what is happening when you are running PCA. Okay, say. You are trying to design a face recognition algorithm using PCA, and as I told, the algorithm you will have to write for face recognition. PCA only will give you the data decomposition in various directions. Okay, say these are all celebrities' faces, so these are our input image, and these are the steps which you will have to follow. Say this is say I have each face m cross n, maybe 256 cross 64, or it could be 256 cross 256. In that case, it will be m square dimension. Okay, but in general, we are telling that this is our input face. First step is to convert that dimension which you have represented in the form of matrix, face you have represented in the form of matrix, just you convert it in the form of a vector. So dimension of the vector would be mn cross 1, isn't it? This is a column, so because column matrix is defined to be a vector. And now suppose we have taken P faces. Okay, so P faces we have taken. Now it actually ideally it should happen. Suppose there are 30 P equal to 30. Okay, but within each, so there are 30 classes. Okay, but within each class, say you have such 1, 2, 30. Okay, so classes are there, and each class would have a number of face of an individual. Okay, you can say 10 faces you have taken, front face, some different orientation, okay, with proper illumination. So to get better result, so that you can take average of all these faces. So you can take a number of faces in each class. Okay, and that has a dimension mn cross 1. Each face has a dimension this, and say these are actually my vector. Okay, so what will be the dimension of this matrix? Mn cross P. Okay, now let us calculate the mean of all these vectors. Okay, let us call it vector, because you understand PCA doesn't understand face. Face is my, if I unfold the face, is my image, but actually it is a vector. So this is a mean we have calculated for P faces, and then say this is my zero mean. This is pre-processing of the data, which is very, very important. You need to do it to get a very good, you now know pre-processing of data. You are subtracting mean, making zero mean. Okay, this we will use afterwards, and then after subtraction of mean, then you have this phase vector. Okay, W dimension is Mn cross P. I suggest you understand this dimension everywhere, so that there will be no confusion. Okay. Okay, and this is actually average phase, which we have calculated the average of all these vectors, and you will get average phase. Okay, and then the most important issue, this is to run PCA, we need to calculate covariance matrix. Okay, and covariance matrix, you know, that after 0 means that is xi minus mu into xi minus mu transpose. Okay, here everything is actually in matrix form. So we have written it. This is the covariance matrix, and P minus 1. My earlier video, you can see how to calculate covariance matrix. P minus 1 because we have samples. Okay, and we are not considering this because this is a constant term. It will not have any importance in calculating the eigenvalue decomposition. So that's why we can just constant term we can ignore. So W is of dimension Mn cross P, and transpose W transpose is of dimension P cross Mn. Now, so then the dimension of the covariance matrix becomes Mn cross Mn. You see, it's a huge dimension. As you can see, if M equal to 256, N equal to 64, okay, or 128 or whatever, right? So it will be really, really problematic to deal with such huge matrix. So that's the reason in 1991, Turk and Peterland, okay, his paper we have referred, suggested a new method based on surrogate covariance. The idea is this. So instead of multiplying W with W transpose, why can't we multiply W transpose with W? Because it is same, means as far as eigenvalue decomposition is concerned, it is same. So if you do that, then what you are getting, that the C, that is incidentally is called surrogate covariance matrix, okay, is equals to W transpose W, and dimensions become P cross P. So if you have 20 images, so dimension of the matrix will be 20 cross 20, 40 images 40 cross 40, which is not as huge as 256 cross 256 or 1000 cross 1000, not like that. So computationally it is very, very friendly. So that's why this instead of finding making eigenvalue decomposition of this matrix, we should concentrate of making eigenvalue decomposition of this matrix. And the relation between the vectors of this matrix and the original one, very easily you just multiply W and then just you can see that how the vectors are related and the eigenvalues are related. So that's not an important issue. Important issue is huge gain you have made in making this trick. Okay, so everywhere you see trick. So we, instead of calculating the covariance of the original matrix, we calculate covariance of the surrogate matrix using this formula. And then on this covariance matrix, we do eigenvalue decomposition. Okay, eigenvalue decomposition we do where it is so suppose now we have V eigenvector, and each eigenvector is attached with eigenvalue lambda. Okay, so particularly the functions are there. If you input matrix, it will give you in descending order the eigenvalue attached with the eigenvector. Okay, so you got this. Now suppose I decide now I will have to select feature, right? I will not take all P. So select k eigenvalue, say in the descending order. So I decide that okay, not all but top k eigenvalue I will select that. So on the basis of this k, generate feature vector psi dimension P cross k, and then we need to generate eigenphase by projecting eigenphase, again eigenvector. Okay, so eigenvector by projecting mean aligned vector to the generated feature vector. So we have k feature vector now, and then I need to project the phase vector, phase vector, mean aligned phase vector. This is very, very important, mean aligned phase vector, that is we have made zero mean, to the generated feature vector. Okay, so we have check always the dimension, yes, correct. So now I am creating eigenphase. This is very, very important. The fundamental is clear that you have P through eigenvalue decomposition of this matrix, and then you have selected K out of P, and then you need to project your data on K. Okay, K dimension data we need to project, and that will give you the eigenphase. Okay, and how it will look like, this is after doing whatever I told, this is what it will look like. So here that's the advantage, you can just see that you are doing the operation, the eigenvalue decomposition, and then projection means what? Again, it's a vector, right? You have several directions, say one direction, that direction, and these all directions are mutually orthogonal. Projection means this vector, say this is v1 vector, v dot v1, we will make the dot product so that we can get the coefficients, okay, the values, to which will show you that in which direction vector has more importance. So these are eigenfaces. Okay, it looks very meaningless for us, but it is very meaningful for computer to tell you the story, right? Then we need to generate signature for each phase. Okay, so eigenfaces we have got, but now for each phase, for example, this gentleman phase, for generating signature of each phase, project each mean aligned phase to the eigenfaces, all the eigenfaces, and say this is omega k cross I, this is eigenphase k cross mn, so and this is zero mean phase mn cross I, okay. I belongs to 1, 2, 3 for p. Hence, this omega will be of the size k cross p after p. So this is all about my training. Okay, so this is the training, and you see here I do not need any level data. So this is one of the rare algorithms which you are studying, which is being trained in an unsupervised way, and PCA can be called as a generative model, and which is trained in an unsupervised way. So it is automatically now getting trained. So whatever phases I have, mean aligned phase, I will just project it to the eigenphases, okay, and I will get this. Now testing. Let us have an image, say a new image. I will have to make again preprocessing, same preprocessing, make it as a column vector, mn cross 1, same size, okay, and mean align I will have to do. So I am doing zero mean, and then I need to project it to the eigenphases to get projected test phase. So I got a test phase PTF, because this I understand, you can see, okay, this image, but this is what computer will process. This is called eigenphase. So projected test phase in the eigenphase domain, right? So it has dimension k cross 1 equals to, we have projected it, okay, and now we have projected the test phase and signature of each phase, and then it looks like, then that is done. You need to calculate the Euclidean distance between projected test phase and each column of eigenphases, okay. So this is our test phase. I need to classify. So what I will do, I will do for each in this matrix, these are my eigenphases, right? So what I will do, I will just make a Euclidean distance between this column and note it down. Okay, say this is distance 1. Then from this I will calculate distance 2. For this I will calculate distance 3. Okay, whatever distance I am getting, I will just keep it d4 like that. Okay, so d1, d2, d3 up to how many are there, k phases are there. So I get all this, so Euclidean distance, okay, right, and keeping it. So it is a similarity measure I can do intuitively. So from this phase, whose distance is minimum, it will be classified towards that class. That's it. Okay, so minimum distance is the matching class. Okay, so that's how it works, isn't it? Great. So you have got the um, uh, classification. Okay. Limitations, this is very important. Proper centered face is required for training and testing. It is sensitive to illumination and scale of face, so you will have to be careful. Front face is required, front view. That's why you take some 10 faces for each class, okay, and take some few front faces so that your algorithm runs effectively. And so these are the two references, that is Greeks, for Greeks. There's very lots of such materials are there, and this is the original paper which talks about the surrogative covariance matrix. Okay. So that's it, how you can visualize. I wanted to give you this example so that you can visualize that when you run PCA, what is actually happening to your data. Okay. So with this, I think you have learned how a generative algorithm works in an unsupervised way to give you a very effective classification. Okay, and in many places, as I have told, that in your laptop, you see, you can develop a PCA-based image recognition for your password. Okay, so you train with your face with different, make sure that front faces are there, and you run this algorithm, and then of course 2 classes will be there, your face and no other, non your face. It will be that simple. So whenever you switch on your laptop, you can see that it is correctly recognizing you. Okay, that's it. Thank you for your attention, and we are coming almost to the end of our semester course on machine learning. So with this critical situation also, we could cover materials, and I hope that that will strengthen your background in machine learning. And these are the tools and techniques, remember, you now know, but how to apply them, for that you need to do some projects and study further, and we'll discuss and come to the discussion forum. And I have already designed an assignment on face recognition using PCA, which I am going to share to you. Okay. Please submit that assignment and enjoy learning your future classes. Thank you for your attention, and stay safe. Goodbye.